So again, you want to look at the factors that influence stroke volume. This dotted line is telling us that it's going to decrease the stroke volume. So peripheral resistance will decrease stroke volume. We also see solid lines over here, and solid lines mean they will increase the stroke volume. So the end diastolic volume, if you increase the EDV, you will increase the stroke volume. That is part of the Frank-Starling law that we're going to look at in just a moment, which is related to stretch. So if you stretch out your ventricle, then you're going to increase your stroke volume. Also, you can increase contraction strength, which is stretch is going to lead to a harder contraction, but that's more from an elastic property. But you can also increase contractility directly without stretching. So this part is not part of your Frank-Starling law. But anyways, this will also increase your stroke volume. So this is everything we're going to look at now. Okay, so the 3 ways to alter cardiac output by changing stroke volume. The Frank-Starling law of the heart, and that really should be capitalized, 2 last names of the scientists that did the work that led to these discoveries. So they found that there's a relationship between your end diastolic volume and your contraction strength. So what they found is that if you have a larger amount of blood in the ventricle, if you have a larger end diastolic volume, it's going to stretch the heart, and that is going to lead to a stronger force to push the blood out. Like an elastic band, the farther you stretch it out, the harder and faster it snaps right back. Okay, and so then that leads to a higher stroke volume. So if you stretch the ventricle muscle, it will respond with more force to push out blood, and then your cardiac output will increase. Okay, so separately, not part of the Frank-Starling law, we also know that peripheral resistance will play a big role in how easily we can move blood around, and that's going to affect your cardiac output as well, right? So if you increase resistance, that means it's harder to push blood, right? So peripheral resistance, frictional resistance of blood flow through the arteries. So the smaller the artery, the more resistance. Also, if you have any narrowing of the artery, this could be due to like buildup, right? You could be getting atherosclerosis, right? You could just have some damage. It doesn't have to be fat and cholesterol deposits, but anything that leads to a narrowing is going to cause more resistance. Being in the cold, right? And having vasoconstriction, that's going to increase your resistance, right? What else? Oh, being overweight, having excessive body fat. That means you have more blood vessels that have to grow through all that extra tissue. And that means now that you have a farther distance for blood to travel, so it's going to take longer. That's also going to increase your resistance. Okay, so with resistance in the arteries, it becomes more difficult to pump blood. And so then your cardiac output will decrease, right? It's harder to pump blood, so you're not going to have as much pumping of blood, right? Cardiac output will decrease. Okay, and the third factor, this is extrinsic control. So outside of the, not part of your vascular system, right? Now you're having input from your autonomic system. And so sympathetic nervous system can increase the strength, right, of contractility. It can also increase the rate of contraction, So increase the heart rate and the strength. And that makes sense. If you're running for your life, you need full blast, right? You need all the blood you can get to your muscles so that you can run as fast as possible. On the flip side, okay, let's finish with this thought. So sympathetic nervous system, increased strength and amount of contractions. So your stroke volume will go up and your cardiac output will also increase, right? I didn't write this for some reason, but you can write this down. The parasympathetic nervous system will only slow your heart rate. It will not have any effect on contractility, okay? Oh, and why? Why is it that the sympathetic nervous system can increase strength? We believe it's due to having more calcium, that the sympathetic nervous system is able to get more calcium released so that you have more calcium available to more sarcomeres, right? And so then all those contractile cells are able to contract even more because now you have more calcium to do the sliding theory. Okay. Next, fluid. Okay, so this is going to be the majority of what we talk about for the rest of this lecture is fluid movement. Okay, so in the body, you want to think about all the fluid in your body. And we're going to look at intracellular, so the fluid that's within cells, and extracellular. And so even though this line right here is bigger and it's showing both interstitial fluid and blood plasma make up your extracellular fluid, pay attention to the numbers. 14 to 16.5 liters. That is less than 27 to 30 liters. So even though it looks like it'd be less visually, it's more, right? So that makes sense. Think about it. Your body is made up of trillion of cells, right? All the tissues in your body. So, and every single cell has fluid in it, cytoplasm, okay? So that makes up 27 to 30 liters. And then all the other fluid is going to be in the tissues, but not inside of the cell, and we call that interstitial fluid. And then inside the blood, or the other thing that's not shown here is the lymphatic system, which is a connection between interstitial and blood. Okay, but the total is here. Okay, so 2 fluid compartments: intracellular and extracellular. And extracellular consists of interstitial fluid between cells and plasma of the blood. And you could put in parentheses next to plasma of the blood lymph fluid, because lymph is going to be delivered back into the blood. It'll become plasma again. So when it's in the lymph vessels, we call it lymph. And then when it gets returned into the vascular system, it becomes plasma again. Okay. Please remember that blood is king. It's in control. It's determining which way the fluid moves, how much. Okay, so we're going to look at different pressures in just a minute. Everything depends on the blood, the properties of the blood. Okay, so it is most important that we maintain proper blood pressure. So you'll see continually, and you may have already noticed so far in class that most everything that we've been studying is about maintaining that proper blood pressure above all else. Okay, so the 2 pressures that we need to focus on will determine fluid volume. Okay, so these pressures are used to determine fluid volumes and movement of water in and out of your vessels. So how does blood and how do parts of blood get out into the interstitial fluid? How does the interstitial fluid return into the vascular system? Okay, so we have these 2 forces: hydrostatic pressure. That's the pressure of the fluid that pushes against the surrounding wall. So think about your capillary, and you have blood, and of course that blood contains plasma. And all of that fluid is pushing against the capillary walls, and that makes it want to leave, right? It's pushing and it wants to get out. Okay. At colloid osmotic pressure, this is colloid just means a suspension of particles. And in this case, the particle that we're talking about is protein. So we're really talking about protein osmotic pressure, but we call it colloid. Okay. And one of the main proteins is albumin, which you already know is huge, and it cannot leave the blood vessel, right? Way too big. There's other proteins there as well that we looked at. You go back to the blood chapter and you'll see different proteins that are in your plasma, right? So all of those are too big to get through the vessel. And remember osmosis, then water is going to want to move into the blood vessel to try to make a equilibrium, because the protein is trapped and it cannot get through. So that is pressure, right? That's a lot of pressure. So there's more protein in the blood than there is outside. The protein's too big to leave, therefore you have all this osmotic pressure of water wanting to go into the vessel, okay? And that's in the opposite direction, right? Hydrostatic pressure was all the fluid in the vessel trying to push its way out, right? It is pushing against the wall, which is fluid that wants to go out of the vessel. Then you have your colloid osmotic pressures going in the opposite direction. So to determine what will move and how much of it will move at what rate, or what the total pressure is in which direction, we have to sum up these two pressures, okay? So we're going to look at components inside the capillary and components inside the interstitial fluid, and then see what happens. Okay, so your book has this image. It's a little much. They could have put this into pieces to make it more visually easy to follow. So that's what we're going to do. So you'll see that all the same information is on the next slides, but it's just done, it's kind of stepwise, so it's easier for you to understand. Okay. So with that said, we are still following the same steps, directions, same method that your textbook is using. Just I'm going to make it look a little visually different. Okay. So if you look at this picture here, you have a capillary. Oh, actually it's a good time to stop to make a short video clips. So let's stop here.